do we do that? Well, we can start from the bottom up or from the top up, and somehow for me it's easier to look from the processor side. So the first lookup is you start from CPU and you look at L1 cache. And it says that H1 is 0.95 and the time is 2 nanoseconds. So AMAT for that level is this time to access L1 and find out if the page is there, plus the miss rate. If you remember not a hit rate, you need the miss rate, so it's 1 minus H1, and then time to look up at the next level. So it's E mat of, I'll call it 1 to 2. And now we need to calculate the E mat of going into next level of cache, which is L2, and that's equal to time to access L2, which is T2, plus the miss rate for that cache, which is 1 minus H2, times the next level. And because we don't have a further, it's only main memory, then it's times Tn. So this total EMAT would be T1 plus 1 minus H1 times T2 plus 1 minus H2 times Tn. And after some math, we get 3.5 nanoseconds. So this is an example to show you how much we got to speed up, because if we went directly to main memory just to figure out where is the address, it takes hundreds nanoseconds. And after all these caches and everything, we still use only 3.5 nanoseconds to find our page. It's a huge speed up. Do you understand why? Basically because this one is much faster and has a much higher hit rate. Basically, it is expected that you will find everything here. So your time won't be only 2 nanoseconds, it will be more, because sometimes you will have a miss, but L2 should save you. But it didn't increase to 10 nanoseconds, it still stayed much, much lower than that. Any questions? We will get to write and read where the memory, and you will see that there is a buffer between CPU and the memory, so that you basically store in that buffer, and the buffer has some registers, so you just dump your stuff there and let the slow process go while CPU reproduces something else. It's on the motherboard. It can be nearby the main memory, but it uses probably SRAM instead of DRAM, or both. Depends on the other base. Yes. Well, you're not speeding up your clock, you're betting on probability. And if probability of going to main memory is 1%, 1% of this 10 nanoseconds is a very small number. So if I do that once in a while, it's not a problem, because everything else is done so fast. That's why you have all these multiplications and additions. Basically, Tn is multiplied with a very small number. So it's not anymore 100 nanoseconds, but something very small, because that's the probability of having to go to main memory. Because if I have to go every time in a main memory, then I would have to have 100 nanoseconds delay every time. But because I'm expecting that only every 100th time I would go there, then, and the rest I will use only 2 nanoseconds, when you add those numbers, it becomes much smaller than 100 nanoseconds. Okay? Any other questions? Because you will eventually have a loop and maybe have to go to main memory. But if it doesn't happen every time, then your average rate is much better than having to go there every time. So, what is the cache organization? Basically, we have to figure out where to place the cache in the cache data that we are bringing from the memory. And we also have to figure out the algorithm to look up and find out where is the data you're looking for. And then we have to check if the data in the cache is valid. Because what if I write something in a cache but I don't write in a memory, or I write something in a memory but didn't store that in a cache? There are multiple combinations, and we will investigate most of them. So let's look first at the direct map cache. Do you have a feeling that this screen is kind of slowly going down? I thought that maybe I'm in sync, but okay. I remember moving it up. So what does it mean, direct match cache? Obviously, cache is smaller than the memory. This is cache decision. So the question is, how do we map multiple addresses to a smaller place? So direct map thing would work like this. You would take addresses from 0 to 7 and map them to the addresses 0 to 7 in a cache. And then you would take addresses 8 to 15 and also map them 0 to 7. And you have to figure out a way to distinguish is it actually 0 or is it 8. So how do we do that? So let's look at the one example. We start with the references like 0, 1, 2, 3, and so on. So at the beginning, you will have a notice, and they're called compulsory notice because there's nothing in the cache. So the first time you always have to go to your memory and bring stuff to the cache. So 0 is not there, we store it in cache, 1 is not there, so. And then you get 1, 3, 0, and they're already in the cache, so you have 6. Perfect, you don't have to do much. Now there is a reference 8, address 8, so now you will basically replace address 0 with the address 8. That's how the mapping works. In a cache, address 0 is shared with addresses 0, 8, 17, or 16, and so on from the memory. And that's also called compulsory miss because it wasn't there before. But now when I want to bring back 8 again, it's called conflict miss because I'm replacing 8 again with the 0. So obviously this is artificial problem. I don't want to have this type of conflict. I have empty space here, but I keep replacing addresses from the address 0 just because I introduced this fixed mapping where that's the rule. So is there something we can do? There are other ways to do this mapping, and we will talk about that, I believe, next class. But just to point out the problem, basically we are replacing the K bit in the cache, although we do have an extra space in the cache. So we'll talk about that, remember that. So now, how do we disambiguate address 0 and address 8? Because they are obviously different in the memory, but in our cache they are the same. Any ideas? You always add something when you have this type of problem. So what would you add? Can I just use a couple of bits to code them? If I add a bit called tag, and say, for example, if it's 0, then this would be 0. If it's 8, then it would be 1. Then I have found a way to distinguish them. Of course, tag in real case would have much more bits, but that's one. The second question is, how how do we know that the page is valid? Which means that we didn't change something in a cache while it's not changing in memory or vice versa. How do we do that with the virtual memory? We have the valid bit, right? So we have a valid bit again, just to tell us if this page valid or not. So now we have a kind of structure how to recognize the addressing in the cache. You have a data, you have a tag, and you have a valid. A valid bit and tag can have more bits. So now how do we interpret this memory address? And I want to show you this type of notation. If this is the memory and this is our cache, if you look at our example, it was 0, 1, 2, 3, and so on until 7, and then it starts with 8, 9, 10, blah, blah, blah. You can see the last 3 bits are always the same. What is the difference are the first 2 bits, right? So our indexing in the cache would go 0, 1, 2, 3, blah, blah, blah. And you can determine the size of that index by taking the memory address mod cache size. Why is that? Basically, you have to figure out how many of these places are distinguished and how many bits it has. So basically, cache index in our case has 3 bits. And then there is tag size, which are kind of intuitively the top 2 bits because they will tell you which page are you looking at. First one, second one, third one. It does not have to be necessarily page, but in the memory, I'm more thinking like, okay, when these 2 bits are going to change, then I can as well think about them as pages. So you calculate that as the memory address divided by cache size. Okay, so if you remember when we labeled this, we said the index goes here and tag goes here in our address reading. Can we do the other way around? What is the consequence of that? If you think about it, if I move these bits up here and have the higher bits later on, what will happen is that basically I will keep switching between pages 0 and 1. And there is an example in a book that shows you that if you have a data and then you have a tag and you have a valid bit, that if you replace the positions of a tag and the index, what will happen is you will start replacing addresses 0, 1, 0, 1, 0, 2, and so on, which are much closer and much more often active than, for example, addresses 0 and 8, 0 and 15, and so on. So the reason why you don't want to switch them because you want to keep the spatial locality. As I said, if I access the address 1, there is a pretty good chance that I will access the addresses on this page. So if I keep switching between 0, 1, 1, 2, and so on, what will happen is I will have too many conflicts, which would make my cache pretty much useless because I would possibly have a miss and I would have to go to a main memory, and that would not necessarily very sense. Questions? So here is the example why I don't want to change the tag with the index. Very important for a test. Any questions? No? Okay. So let's move on. What type of hardware do we need to realize this direct map cache? Obviously, we need to read the memory address. So we have a cache tag and cache index. And the first thing we have to compare is the cache tag with the tag that we have in a cache to find That's how you search through the cache to find the address you're looking for. So once when you do that, then you have to check the valid bit. So if this is true, then and valid bit is true, then you have a hit. And then you let the data to CPU. If it's a miss, then you go to a next level of cache associated memory. Questions? Yes. I'm sorry? How does the tag help? Well, as I said, how are you going to distinguish is it 0 address or 8 address? The tag will tell you by the difference between these two bits. Basically, when you have a memory is larger than cache. So when we did the direct mapping, so this is the smaller cache, this is the large memory. And you have, let's say, top 8 addresses and then the next 8 addresses. And you're mapping them to the same space. So once when you map them, you have to have a way to distinguish is it address 0 or address 8 mapped on my address 0 in the cache. So that's why you need the tag bits. They tell you which actual, you can think about that as we had before in virtual memory converted between physical memory and the virtual memory addresses as a lookup table. Well, these bits are lookup table for the between physical memory and the cache. You need to distinguish which set of addresses are mapped into this cache. Okay? So, what if so far we assume that we have a word addressing, for example, so each address has one word. What if I want to have a byte addressing? Am I going to make each of the addresses in the cache byte addressable, or I want to do something else? Wild guess. Remember we talked about spatial locality. So actually you don't want to make it smaller granularities. So I don't want to have one address here to address one byte. I want to address as much as possible. And usually address one word, which is 4 bytes. But then we need a way to actually find which of those 4 bytes do I want to use. So I need a byte offset for that. So I'll have a cache tag, cache index, and byte offset. And we'll see later that I actually want to take even larger chunks because of that spatial locality and group them into my cache. But we'll get to that. So let's solve one example. So what example says? It says, let us consider the design of a direct map cache for a realistic memory system. Assume the CPU generates 32-bit byte addressable memory addresses. Each memory word contains 4 bytes. A memory access brings in a full word to the cache. As I said, it brings the full word, but we still want bytes. The direct map cache is 64 bytes in size. Compute the additional storage space needed for the valid bit and the tag field of the cache. So as you can see, we don't bring only bits for our data in a cache, we have overhead, and we want to calculate what is the overhead for a valid bit and cache. So since we are bringing the words into cache, but we need to address the byte, we need the byte offset. So how many bits do we need for that byte offset? 4 bytes, 1 word. How many bits for those 4 addresses? 2. Great. So we take 0 and 1 bit for the byte offset. now we need to figure out how many bits do we need for a cache index and what is left to put in my cache tag. So if you remember, I said the number of cache entities is calculated as the TIC64 kilobytes divided by 4-byte words, and you get 16 kilobyte entry. That's the size of each entry in a cache, and in order to address that, you need how many bits? 14. So that means from 2 to 15 I have cache index, so the rest is left for the cache tag, and on top of that I need 1 bit for a valid bit. So the total space would be 17 bits times 16 kilobytes for each cache entry, and that's this size, and the total space for the data was 64 kilobytes, so this is how you calculate that. Is it time for a break? Okay, 5-minute break. Are we ready? Okay, so let's see how our pipeline changes because of these new caches that we introduced. So how did we replace the memory stages? Well, we don't call them generally anymore DMEM and IMEM, we call them Dcache and iCache. Just to point out that they're very fast memory elements. What do we do if we have to access iCache? And it happens that our address is not there. What do we need to change in our pipeline process? If we have a miss, then we will just insert bubbles in our pipeline until we bring the address from the L2 cache or general memory. But if miss happens in Dcache, again, what do we need to do? Well, actually, we will stall a write back stage, and we actually insert bubbles there, and we can stall these addresses or flush them if they are damaged. But usually, because they didn't use the memory, they're probably valid, so you can just stall them in their own stage until you bring the address that you need and finish your operation. Okay. So now we're getting to read and the write access to cache. How do we do that? Well, the first thing is CPU sends the index to cache to see if the data is there. And if it's a hit, then cache sends back the data. And this is the picture how it looks like. You have a CPU, index and tag, you find the address in cache, and you send the data back if it was a hit. If it was a miss, then what you need to do is, again, you have to send the index tag to cache, look up, find that it's a miss, so you send it back. CPU sends the address to the main memory. Main memory finds that address and sends the data back, and sends it to both CPU and the cache. Okay? Now, what you need to note is that if there was a miss and there is a request for the main memory, all that happens in the same cycle of a pipeline, regardless of is it fetching state or memory state. And upon sending the address to memory, CPU sends knobs down the pipeline so it can wait until it gets its address. Any question about reading? No? Okay, how about writing? Is that faster or slower than reading? It depends what happens. Here you just have to fetch the address and fetch the data and send it back to CPU. Either it's in a cache or it's in a memory. When you're writing data, there is a question, are you going to update only a cache, or you're going to, CPU is going to write only into cache, or it's going to write both into cache and into memory. So if it's writing in both, memory is much slower than the cache, so how do you synchronize these two processes? So that's why there is a difference, and that's why we have two policies. One is write-through policy, and the second one is write-back policy. So write-through policy says that CPU is writing in both cache and the main memory any update it produces. So let me show you a picture. It goes this way. CPU sends the address and sends the data into both cache and the memory. That's a write-through policy. In each write, you have to set a valid bit to 1 so that you know that it's valid page, it's updated. And each write goes to memory, and as I said, it goes through write buffer. Why it goes through write buffer? When you are writing data into cache, it's very fast, but if you're writing that into main memory, it's slow. And you don't, basically, there is no point of having cache in this case if you have to wait for the memory to finish its job. So what you do is you kind of insert write buffer in between, which is a certain number of register type storage, which is very fast, and you just dump your results there and let that unit communicate with the main memory with their own speed. But your CPU is not busy with that task anymore. It can do other stuff. Now, what happens is if a write buffer is full, which means you have been writing a lot, and you filled the buffer and you didn't have time to finish writing things off in the memory. So what do? Yeah, you have to stop everything and end the stall pipeline until that's done. Any questions? Okay. No, until you get the first free space. You don't have to wait the whole thing to be empty. It would be good if you would knew ahead of time that you will be storing 3 or 4, then you can just wait once for 3 or 4 to leave and then keep writing them in. But you don't know what will be next instruction and what will happen. So yeah, prediction is a pretty nice thing. Unfortunately, we're not really good in predicting future. So there are 2 options in write-through policy. Each write goes to cache, and tag is set and valid bit is set. And this is called write allocate. There is also no write allocate where cache is not written to if there was a write miss. How that helps? Any guess? What happens if there is a write miss? Yeah. So why wasting time and waiting for that to clean when you can just not write and skip it completely? So there is the second option, which is called write back policy. And that write back policy says that you write to cache and you don't bother to update the main memory. Can we do that? Well, the first question is now our memory and cache are not consistent. They have a different information, so we have to do something about that. The second question is, will we ever have to write to a main memory? Yeah, eventually you have to get that information out. So basically, what you do is you start with updating only cache, and let me show you the picture. Oh, actually this one. and it's not very nice picture. So let me explain what happens. On each CPU, write, it's written only in the cache, and CPU cache interaction is same as for write through. Basically, if it's a hit, it brings back the data. If it's a miss, it has to go to the main memory. The difference is that now to distinguish, do we have same status in main memory and the cache, we introduce a dirty bit. And dirty bit means that if it's set to 1, content in cache is different than the content in the main memory. It works very similar to valid bit. So cache clears the dirty bit upon processing a miss that brings memory location into this cache entry. And in this case, you would think that we don't need the write buffer because CPU is not going to write to memory that often. And that's correct. But you can use that write buffer to service a write miss. How would that help? Why would I use write buffer for write miss? You can bring stuff from the memory to write buffer and actually have a couple of them so that you can look up things faster. Okay, so let's see what has changed in a write back policy in terms of hardware. We still have a cache tag and we have a cache index. And we again compare tag here with the tag in a cache, and if it's equal, and I again check the valid bit, it's a hit, and I let data through. Now I also have to look at the dirty bit to find out if when it's a miss, to synchronize the information between main memory and the cache. So let's compare these two policies. Write through, obviously cache logic is simpler and faster, creates more bus traffic. Is that a good thing or a bad thing? Bus traffic. Bad thing. You're creating more potentials for a hazard. So with the write back, you require dirty bit and extra logic, but it's much faster. And the compromise is actually to use them both. And you use L1 as a write through and L2 and L3 as a write back. Why would that make sense? Hmm? Yes. And for the other two, you're not using them as much, so only when there is not enough space. And they're also larger, which gives you a chance that you will have a less misses. For example, with L1, once when it's full, then writing into cache will start having write misses, so you have to go to a memory. Yes? No, I believe it would go just to main memory. Because if you do that, then you would keep the copy of L1 cache into 3 different spaces, and you don't really need that much redundancy. It helps with reliability in a sense that the more copies of the same thing you have, the better chances of recovering if something disastrous happens, but usually 1 to 2 spots are enough. Okay, any questions? So let's see how do we deal with the read miss and the write miss. So this is one example where we obviously have a read miss between I1 and I5. This one is loading this word and this one is reading it. So how would we treat that? This is pipelining, you know this. Yes, so what do we do? Well, we can insert the knobs and stall the information in decoding stage, or we can use busy bit, forwarding, and kind of speed up the process. So basically, we'll treat this as any data hazard. No, but what happens is if I don't have a space anymore in a cache, that's when you have a write miss. I want to write something in a cache and I don't have a space. Okay, so what? Actually, for a read miss, it means that it's not in the cache. So you have to bring that information from the memory to the cache and CPU at the same time. And for a write miss, what do we do? Well, if we have a write buffer, it alleviates the problem of misses. And we have that with the write through with the write allocate approach. So basically, that's not the problem because you have a write buffer. But if you have a write back, what happens if we have a write back policy? It will be treated the same as a read miss. Pretty much you will have to use the busy bit and the forwarding or just insert knobs depending on what type of realization do you have. Okay? So let's see what is the execution time with caches. It's like we're slowly going backwards and filling up the gaps. We talked about pipelining, and we said we have some sort of memory, but we treat it as a black box. Now we know what is the memory. It's a cache. It behaves a certain way. We saw how it affects the pipelining. Now let's see how it affects execution time. So before we had that execution time is equal number of instructions times averaged time that you need for each instruction and times cycle time or frequency of the clock. What would change now? CPI would be calculated differently. Why? Because now the average instruction time is different whether you have a hit or miss, right? So basically you would have a CPI average plus memory stall averaging depending on did you have a hit or miss. And execution time total is number of instructions times CPI average for the instructions that don't deal with the memory, and then M stall averaging times cycles. So let's see how we calculate this memory stalling. It's miss per instruction average times miss penalty averaged. Why does it make sense? Well, you have to calculate how many misses do you have per instruction, and the penalty is how long it takes to recover from the miss, to bring actual data. So now the total memory stall would be number of instructions times memory stalls. Let's solve one example. It says, consider a pipeline processor that has an average CPI of 1.8 without accounting for memory stalls. So this CPI is this CPI average, then I'll write here. That one is 1.8. And then we have a I cache, has a hit rate of 95%. Okay, and D cache has a hit rate of 98%. Okay, so what else do we know? Assume that memory reference instructions account for 30% of all instructions executed. Out of these, 80% are loads and 20% are stores. On average, the read miss penalty is 20 cycles and write miss penalty is 5 cycles. Compute the effective CPI of the processor accounting for the memory stalls. So, what is our first step? Effective CPI is always the base CPI which is in my case the CPI average. That's how long it takes for all instructions that do not interfere with the memory or interact with the memory. Then they are D cache CPI plus I cache CPI. So how do we calculate each one of them? Well, for base CPI, as I said, it's 1.8. For D cache, we have to calculate the cost of write and read. But let's first do I cache. Why? Because it impacts all the instructions. All of them have to be fetched. So cost of instruction miss is I cache miss rate times read miss penalty. And read miss penalty is because in fetching state we are only reading the instructions. We are not writing anything. So in our case, I cache hit rate is 95%. So the miss rate is 1 minus HI, which is 0.05. And we need read miss penalty, and it says it's 20 cycles. So I cache CPI is equal to 1 minus HI times 20, which is 1. Okay, for Dcache, we have to separate the cost of read miss and the write miss. Why? Because in that stage we can both read and write. So the cost of data, if you look at here, it says that assume that memory reference instructions account for 30% of the instructions. That's why we have this 0.3 here. And of those 30%, 80% are loads and 20% are stores. So for a read, we have 80%, 0.8. And then the miss rate is 1 minus 0.98, and the number of cycles as a penalty is 20. So we get this number. Any questions so far? Okay, let me kind of write it down. So we have a CPI for Dcache, and this one is for read. And we have 30% of instructions that are used as a memory reference, and 80% of those are the read instructions or loads. And the miss rate for Dcache is 1 minus 0.98. And for the read, penalty is 20 cycles. Now for write, we have again the same 30% of instructions are dealing with the memory. 20% of those are stores. So here we have 0.2. The miss rate is the same for Dcache, 1 minus 0.98. And the penalty for write is 5 cycles. So that's how we got all these numbers. And then finally, when you substitute them back, you get this number. Questions? Okay, so the bottom line is that improving miss rate and reducing miss penalty is the key for improving the performance. Basically, you want to reduce these numbers here, and you want to improve these numbers here. because for the rest you pretty much have no control over it, but the hit rate and the miss rate you want to improve, and you want to reduce the penalty, how long it takes to recover from the miss. Questions? Mm-hmm. Okay, so if you look at here, it says miss penalty is 20 cycles, and if you remember here, we had the memory stalls, which is misses per cycle times miss penalty. Misses are 1 minus 0.98 or 1 minus 0.95 for a different for D cache and I cache, and that's given in the task. And then you multiply that with the miss penalty, which is 20 cycles and 5 cycles. It's kind of right to write equation with all these numbers. That's why I explained for each number explicitly where it's coming from, so that you understand. The problem is that not all instructions are dealing with the memory. That's why we have to specify which % of all instructions are interacting with the memory. Most of them are addition, subtraction, and you don't really worry about them. That's why you have this average CPI of 1.8 without accounting for a memory stalls, because most of instructions do not interact with the memory, but those that do will be impacted by the hits and misses in the memory. And you separate D cache and I cache, because I cache only deals with the read misses, while the D cache deals both with the read and the write. If you remember the pipeline, I cache is only fetching the instruction. So you have to read in a memory what is the instruction, while the D cache may have both read and write, and they have a different penalties. So that's how we calculate the whole thing. Questions? No questions, or you didn't understand the word of what I said? So the goal is to have a new effective CPI that takes into account regular instructions and those that interact with the memory. And for them you have to calculate it slightly differently. Okay, if you have no other questions, that's all I had for today. I'll see you Thursday.